Yes. So just 1 minute, please. 1 second. Signal or no? Okay. Yes. This is very good project. In fact, sentiment analysis. So you can start. Okay. So sentiment analysis. It's a sequence. It's a sequence to one, for example, or many to one. So we have a sentence, for example, or like review, for example, which we had an example before, and we need to make some prediction. Is it positive or is it negative? Or also we can classify it to some topics, similar to the problem which we got from the predators. So Jubair, can you hear me?
Yeah, so I was thinking doing a project on natural language processing so that it helps my background as I'm from business background. So mostly I was hoping like I have two data set. One, I'll give the link of data set below. Uh, one of Irish song lyrics and one of sonnets by William Shakespeare. And we also have the dataset from IMDb for classifying the reviews, like a positive review or negative review. So I was thinking of working on this data set and tuning it up and using it like different models to analyze the accuracy rate of this sentiment analysis project. So first I've given some basic definition of sentiment analysis, like it's a text classification tool that analyzes an incoming message and it understands the sentiment, but there are some challenges which I think we need to overcome. For example, it cannot understand sarcasm or emojis and other stuff like subjectivity, tone, and irony. So these are the things I think we need to work on. And I think if we fed the enough data to the model, I think it will be like sometimes it can understand. For example, we can all understand the sarcasm level of Google Assistant or Siri nowadays. It's really, really good. So this is the link of the data set. Two links and the IMDb dataset. I didn't put it here, but it's widely available in the online. So the pseudocode is mainly about the project is like we initialize a tokenizer, which converts input text to a stream of tokens. For example, if we have a word, uh, for example, if we have this line, initialize the tokenizer, which converts input text to stream of tokens, and a tokenizer actually tokenize each and every word, so and puts it in a dictionary. So there's an easy method on Keras, which is called fit on text. It actually does this whole thing without even bothering us in going through the whole process manually. It actually fits it the whole way and it creates the word index dictionary. Then we will look through the input sequence using the text to sequence method, which takes each text in the word and replaces it with an integer value from the word index. So if there's a repetition, it probably will skip it. So that's uh, one of the constraint of this method, but still it's real for preliminary purpose, it's okay. Uh, I was thinking of preferring a model of LSTM, long short-term memory. Uh, the choice of my preference is because in natural language processing, a sentence is not complete until you have like the full context of it, and If we use any other method, it's mostly it's gonna lose context in the long term. And there are some sentences we know that we need long-term dependencies. So that's why I was thinking of using an LSTM, mostly bidirectional LSTM. In the next slide, I have some code glimpse. Yeah, so here we initialize the tokenizer and we put the data into all of lowercase, just in case we have any problem with the word index. Then we call the fit on text method. The next, we iterate through each uh, word index and call the text to sequence method. And we append the sentences. Then we create the labels for X and labels with the input sequences. And then we call the to categorical method to categorize the number of total words. I think there were uh, 20 or 25 words here. I don't have the output here, but I can give it later or send an email to it. Then we build a model with input equals to the max sequence length, and then add a bidirectional LSTM with a dense layer. Uh, by the end of Epoch 500, we had an accuracy of 94%, and that's it. Any questions?
This is very good, in fact, very, very good, because we didn't start working here in LSTM. So, so any questions for any questions to Japan? Yeah. But how can you guarantee that you don't have overfitting or something? Do you have the graphs for, I mean, training and you have a very small data set?
It's the graph for training and validation.
Yeah. So I'm asking, can you go back to the code one more time? So you used this sentence for, can you go up, please? So you used this data. So this is my corpus,
Yeah,
this one. And the tokenizer, it will be trained on this one.
yeah, on
So
this one.
we will build a dictionary for this one.
Yeah, word index for this one. It's actually a long text. I shorted it down just so I can fit it on the screen.
Okay, and what will be the sentiment here, or you try to predict
No,
the next
I'm actually trying to predict next
word?
word. Yeah, here, but it's mostly the same structure for predicting the sentiment. You put it in a tokenizer, you load the script, you fit the text, and then you call the text to sequence, and then you build the model.
Can you go please to the LSTM?
Yeah.
So what is the difference between bidirectional and
in the normal LSTM, information actually flows in one way. So you can have the past preferences, but it's preferably not that like uh, it's not that healthy information in one way, one directional LSTM. It's okay, but in bidirectional information flows in both ways. Like you can go back to the past and check whether if you need any words or any important information that you left before. So I think that's really good because if for a sentence or for a text, we also need to have the context, and sometimes text can be really long. So it's important we look in the past to figure out what will happen in the future.
What does 20 mean here in LSTM?
This is the number of layers.
Number of layers or number of hidden states?
Hidden states. It's mostly, I think, gates. Number of gates. Yeah.
Okay.
As gates control the information of the past, and future. So I think it's the number of gates.
Mhm. Total words here, it's the length of
Yeah,
the
it's
text.
the length of the data set.
Mhm. Oh, so we get the probability of the
Yeah,
next word. So now I understand.
yeah,
Mhm. So the output, in fact, it will be one hot encoding. So he will try to predict the probability of the next word. So if you
yeah.
said how are, so we are expecting that it's you, for example. So we will try to predict the next word. So you used this data set for training the model. Uh, is it possible to use a different one, for example, for testing?
Yeah, sure. It's like it
So for
will be
example,
a bit difficult because just there will be one problem because the data set I use for training, the words it will have in its word index. If I used a different data set for testing, if there's any word that the data set for training does not have, it will flag it as a zero or null. So it
okay.
won't understand that word. That's the only problem with this natural language processing.
And is it possible to train the embedding mode embedding alone? Is it possible to or use transfer learning so we can get
Yeah,
a
I
way?
actually used the transfer learning in another, like this is the simple one for predicting the next word. I used the transfer learning for predicting the next line of sonnet by William Shakespeare. So it's in a different project. I'm working on it right now. I can share the code if you want.
But it will be very nice, Jubair, this is very good work, but it will be nice if we can try to build a demo, for example. So now we are using text. We can use speech to text, text to speech, and we can just try to build something which you can, I mean, use natural language for. But it's very good, very good. So what will be the plan for the next part?
Sorry.
I mean, what will be the plan for the next part of the project?
I'll be writing a whole description for the project and I'll with the code and I'll give the like particular applications of this project in the real world scenario,
Mhm.
and I'll give you an project file by the end of probably this month.
Okay. And is it okay for you to share are you using Colab or
I'm using Colab. Yeah.
is it possible to share it with me, for example, so I can share it with the rest also? If you like. If you don't like, it's fine.
Yeah, of course. I can share the code. Like I
Maybe the
can.
sample one. Maybe the sample version, so people
Yeah,
can.
sure. I can download the Py file and forward
So
it to you.
yeah, so students can. I mean, people can start to play with LSTM.
Yeah, sure.
It will be also very nice, Jubair, because you are from business. So I know that you are interested more also in time series, stuff like this. So if you can have an example, for example, for a time series prediction using LSTM, it will be very, very good.
Uh,
Because because
Actually,
you
I'm doing my thesis on a time series of prices of oil, but it's mostly on statistics. So I think I'm gonna finish my thesis within this month, and then
but
I was planning to work on recurrent neural network to predicting the future prices of oil
I guess
with
this
my data
this
set.
this one will be very, very good, very good. What is the size of the window? I mean, how many old values do you use, historical values to use? Do you use for predicting the next price?
I'm not sure, but I have like almost 3,400 prices from 2008 to 2020. I think it's good.
So are you using autoregressive, for example, for
Yeah,
predicting?
yeah. I'm actually using co-integration to checking whether the oil prices and carbon prices are moved together, like their means are constant or not.
Mhm. Okay, this is very good. I guess this one will be exciting because when you apply it in your field, it will be really very maybe. Did you check literature review as well? If it has been done before?
Which
Some people
one?
use, I mean, people use LSTM or
On
recurrent neural network for.
on oil,
Mhm.
on predicting future prices.
Yes.
Yeah, I have seen a couple of people using like recurrent neural networks using uh, in what do you call it? Uh, stock trading. because of the like price tricks and something. So I have read a few papers, but I never applied myself on this time series.
But you need to start because they know, I mean, people are working around the world and people are
Yeah.
very. So if you want really to publish something, you need to be very quick. So
I will
if you
start
tried
as
already in your publication, for example, you have been trying now statistical approaches, you can also use RNN, for example, and try to make comparisons.
Yeah, okay.
It would be really very good. It will be exciting for people from finance and people also from machine learning area. Yeah. Okay, thank you very much, Jubair. Thank you very much for this.
Thank you.
Yeah,
Okay, I'm gonna stop sharing.
Thank you.
Thank you, Joel. I have a question.
Yeah, sure.
Thank you for your presentation. How long take time to reach this box 500?
Sorry.
How much time it takes?
If you use a GPU, it would take like 10 seconds, I think.
Okay.
But you have to use the GPU, otherwise it takes like 10 minutes.
You are using GPU from Colab.
Yeah, I'm using GPU from Colab.
Okay. Did anyone manage to run Colab code in local runtime? Because we can select a GPU, but also we can run it in our computer. But there's some setup which we need to do.
Yeah, there's a runtime option, change runtime, where you
Did you try to use it? Did you try it?
Yeah, I'm actually trying. I work on GPU if I need like work on a heavy project.
Okay, because I have a problem in my computer. I try it, but I have a problem in something called OpenSSL. And I've been discussing it yesterday with Mohammed Saad. But it's not working in my computer because of some problems. But I wish if we can test it because I have been running a code and the GPU allocated to the virtual machine in Colab, it's not enough. They claim that it's 12 GB, but I don't know. I had a problem also in one of my code. This one, it's just 8 GB. So maybe the one in Colab, it's much better. But I'm not sure also if it is 12 GB or not.
I used Jupyter Notebook on my computer, and then I could access my GPU. So I was able to just take the code from Colab.
But also from Colab, you can connect to the runtime.
I haven't tried it.
I have been trying because it's easy to install it. I need to fix the setup, but I have a problem in my installation here in my computer. I got an error message, something called OpenSLM something, which I couldn't fix in fact. So thank you very much, Jubair.
Thank you.
Thank you. I guess we have also, I don't know if, need to check. Maybe he is not online. Okay. So is there anyone who want to have a presentation today or something to talk about his project? No? No updates? Okay. Because we have also Masoud, he prepared something in fact. So he prepared some slides. He prepared something in RCMM, but I don't know if he is online or. Do you know him? Okay, so he's not here. So in this case, we will just maybe he will present. He preferred to present it next week, but he prepared very nice presentation. In fact, in RCMM and different versions of RCMM. I guess he is offline. So maybe next week he will present it. So I guess we can go back to our lectures. which is So it's I mean we started this one maybe 2 weeks ago, and we have been going through. We started last time with this example for this MNIST data set, and we try to use. It's a shallow learning as well. MNIST data set. So MNIST data set, it's 20. Its pixel size is 28 times 28, and it's 70,000 data points. We use 60,000 for training and 10,000 for testing. And we can build a model using a Keras, for example. So here we have 3 layers, 2 hidden layer and 1 output layer. We used ReLU. No, it's two layers in fact. So we used, 1 hidden layer and a drop out layer. And also we used an output layer with 10 outputs because we have 10 classes. We did that, and we can also define. We can define an intermediate model, or if we need to plot the output from an intermediate layer. In fact, we need to define. We need to use model API. So you can define your model as a sequential. By the way, did you make comparisons between sequential and model API?
No, just I'm making comparison between different strides in functional API.
Functional API.
Yes, the different between the different type of strides. And I found something defined me and Ahmad. When the stride is increasing, the accuracy will be decreased.
Accuracy will be decreased.
Yeah.
This is very good.
Yes. I found, and in the next week I plan
to have presentation. So when a stride increases, it means we are moving with bigger step.
Yeah.
So we try to reduce the overlap, and when we reduce the overlap,
and also there is I think correlation between the batch size and the stride. When, for example, both strides and batch increase, the time will be decreased very much.
Yes. Do you know why? Because we will adjust weights one time each batch size, and then when the batch size increases, how many batches?
128.
This is a batch size.
Yeah.
So I mean, if you need to define how many batches, we need to divide the size of my data set by the batch size. So this one will be the number of updates of my weights, correct? Yeah. So when number of updates decreases, it will be faster, right?
Yes.
So time will be less. So now we can understand why when batch size increases, time will decrease because number of updates will decrease.
Yeah.
Right? Yeah. If you want to make it, I mean, you can just choose batch size equal to the data size, which is full batch or batch gradient. We call it batch gradient, not mini batch gradient. So when it's in batch gradient, the batch size will be the size of my data set. And in this case, we will adjust weights only one time each epoch.
Yeah.
But when the batch size is 128, for example, so how many times we will update weights? It will be the size of my data set divided by batch size. It will be number of updates in each epoch. And then when you reduce the batch size, number of updates will increase. So it will take more time.
Yeah, exactly.
So this is a connection with time.
Yeah.
So this is very, very important. And if you can also make comparison between model API and sequential API or functional API and sequential.
Yes, you told that in the previous session, it's not possible to make a precision because
no, you can make comparison of all parameters.
Yes,
are the same.
But in the functional API with strides, we have to change the strides. But in sequential one, the stride is the same.
No, you can choose also. You can define
sequential.
In sequential, you can define it, right?
Okay.
Because it's a parameter, it's hyperparameter. You can define it.
Okay.
So just to make comparison between sequential and between functional, using the same structure, the same hyperparameters, all are the same. And we will run this one, and we will run this one. So we can, but also running it one time, maybe also it's not good. maybe you need to run it 10 times and it takes average. Because maybe while I'm running it, my computer was sending some emails, was doing something else. So you need to run it several times, takes average to be sure that this is the average time for not only one time, because maybe one time, maybe it will be too high or too little, we don't know. So we need to run it several times and it takes average. So we used this example last time, and we used this model ADI to plot in the intermediate outputs from one layer. So we can plot the output from, so the input here, it will be model input, and the output will be the output from the hidden layer. The output from the hidden layer. So we can plot the output from each layer. So data representation for neural network, we talked about this last time. So if you want to calculate how much memory do we need, if your GPU is 8 gigabytes, for example, so we need to be careful about the batch size. So each time, we have here a batch size, in fact. So each time we will have here a batch size. So the batch size here will be very, very important, right? Because if you need to calculate how much memory I need to handle this data to this batch size, because this is very important, right? So I need to multiply this one by this one, by this one, by this one. And if it will be stored in, for example, 32 bits, so we can calculate how much memory we need. So in this case, we can decide what would be the batch size. When the batch size increases, memory will decrease, so maybe your computer will crash, right? And I have it I'm running something here, a very simple example. It crashes all time, right? Because of this memory issue. So need to be careful. If you want to calculate how much memory, you can just do it from here. Batch size multiplied by, the image size, for example. If it is RGB, this one will be 3, for example, and so on. So you can just calculate. If you will store it in 32 bits, so you can calculate how much memory we need to for our batch. So it will be nice. If this information is in a publication, for example, it will be exciting. It will look more professional, in fact. So we talked last time about, it's similar to Jubair example. So Jubair is working with LSTM, but here you can just work with normal feed-forward MLB, for example, multi-layer perceptron. And this one, it's internet movie database, and we have a text, and this text has some label. Label is negative, maybe positive, neutral, whatever. So we need to build a model, or we need to train a model to make this classification for reviews. So the reviews, it's different, the size is different. So if you will use MLP, we need to fix the size. But if you will follow Jubair approach working with RNN, so it will be a sequence. We don't care about the sequence, the length. But if you will go for MLP, no, the size is very, very important. So you need to decide how we will represent, how we will code this one. So you can just say, okay, I will select the most popular 10,000 words. So in this case, and we will build a dictionary. Each word will have an index. So in this case, I can just convert this review into a vector, a fixed size vector. It will be 1 when there is a word at that index. The rest will be zeros. So the length of this vector, it will be 10,000 values, and it's binary values. And as Hamed mentioned last time, because some words are repeated, for example, so you can just count number of words, and you can just normalize later on, or you can just put 1 when it appears for the first time, and ignore the rest, ignore repetition. So the length of the vector, it will be 10,000 values. Maybe 10,000, it's too much, so you can just use word embedding and try to convert it into a shorter vector. For example, Jubair here, he selected 64. So we will code it into a vector of size 64, for example. It will be float values. So now each one of this, but we need to train a word embedding. We need to train a word embedding. Each one of those 10,000 vectors, it will be converted into a vector of 64 values. And after that, you can just feed this one into MLP. The output will be sometimes negative, positive. So it's 2 values, it's binary classification. So you can just use softmax or Gaussian activation functions, right? And to train your model. So this one was an example also. Maybe Jubair can try to use this one and make comparisons between MLB and RNN, for example. We have here a very simple example, I guess. We have here some very simple examples and the accuracy. So this is, for example, one review, an example. And we need to encode it using our dictionary. So we have 10,000. We will pick only the most important, most popular 10,000 words. In natural language processing, they can find it. So they draw the frequency of when the word appear, how many this word will appear in the whole text, and you give it frequency, and you can just select the most important, most popular 10,000 words. We will give each word an index, and after that, we will just replace this one with 1. The rest will be zeros. So it will be 1 when this one appear in the text, otherwise it will be zeros. So now we can get this nice vector, which is still too long, but it's fixed size. You can just use this one as an input, or you can try to use word embedding. Sorry. So I trained a model, very simple model. So it will be, input layer, it will take 10,000 values, and we will have some layers, and the output will be 2. So the output layer here, we will use sigmoid, and we will have 2 outputs. And we will just train the model, and the model will be able, it has, just for 3, 4, 5 epochs, we can get 87% accuracy. Yes. This one also, this data set, it's a multi-class. The other one was binary, but this one, it's multi-class classification. So we have here number of classes or number of topics. In fact, it's a news. This news wires, those news wires, it has topics. We have 40 topics or 46 topics, where some topics are more represented than others. So each topic has at least 10 examples in the training set. And the data consists of this number. So we can just use this one for training. In this case, we need the output layer would have 46 outputs, right? And in this case, we need to use softmax. So it is the same also. We can just pick the most important, most popular 10,000 words. We will build a dictionary. Each word will have an index, and maybe according to importance. So maybe the first word has been repeated a lot in the text. So it's by frequency. In fact, we sort it according to the frequency. How many times this word appear in the text. So finally, we will get this this one, and this is the topic index. The output will be like this one. It will be, we will use one-hot encoding, so it will be 1 when it's topic index, for example, 3. The rest will be zeros, and we will build a model, and we can get accuracy also. Maybe the accuracy, as you can see here, for training, for testing, it's maybe 76%. So in 40, in maybe 20 epoch. So it's nice. Convolutional neural network, it consists of, the architecture consists of 3 types of layers. We have an input layer, right? We have an input layer, feature extraction layer. It's a repeated sequence of convolutional layers, and the pooling layers, and the classification layers, or fully connected layers. What is pooling? What is pooling? Pooling layer?
Pooling layer? Much pooling in order to decrease this
downsample.
Yes.
Yeah. So downsample, or
and also for decreasing the probability of getting overfitting.
Yes, correct. Yes. So 3 types of layers in CNN: convolutional layers, pooling layers, fully connected layers. Convolutional layers are composed of filters and feature maps, right? We have filters. We need to decide. The filter size. It will be a hyperparameters. We need to decide, and the output will be feature maps. And maybe convolutional layers, the input will be the original image only when it's input layer, correct? When it's close to the input, and the other will just use the feature maps. Filters, the filters are essentially the neurons of the layer. I drew it here last time, how it will look like, correct? So if you have 3 times 3, you can just, if you have a filter size of 3 times 3, and if you have, for example, 32 feature maps, you can just imagine that each filter is a neuron with 9 inputs, 9 weights plus 1 pipes. So they have both weighted inputs, and they generate an output like a neuron. The input size is fixed, a square called a batch or receptive field, right? This is the receptive field. When the receptive field is much wider, for example, the stride, it will control how this receptive field will move across your image. If the convolutional layer is an input layer, then the input batch will be pixel values, correct? if they deeper in the neural network architectures, then the convolutional layer will take the input from a feature map from previous layers. So sometimes it will deal with original image, and sometimes it will deal with, when it's deeper, it will deal with feature maps from previous layers. Feature maps, the feature map is the output of one filter applied to the previous layers. I explained it last time. So we will have an original image, we will apply the filter, and we will scan it, we will move by step size, which is stride, for example, and we will scan it. Each time there will be some activation. We will activate, correct? Each time will be activation. So that is why when you increase the stride, number of activations will be less, right? Number of activations will be less. So, and that is why time will be less. So when you increase the stride size, the running time or training time will be less because we are just perform less number of activations. If the receptive field is moved 1 pixel from one activation to activation, then the field will overlap with the previous activation by field width -1, correct? So the overlap. So if it's a 3 times 3 and the stride will be 1, so how much overlap? It will be the receptive field width -1, so it will be 2. There will be overlap by 2 each time, correct? Because we are moving with 1 step. If stride equal 2, so the overlap will be 3 minus 2. So this is the filter width -1. The distance that the filter is moved across the input from the previous layer, each activation is referred as stride. Zero padding is used to invent mock inputs with 0 values for the receptive field not to read off the edge of the input feature maps. So if you need the feature map to be the same size as the original input, we need to have those 0 padding. 0 padding means we will add some column and rows with zeros across to just keep the same size. So this is an example. We have a kernel which is 2 times 2, and this is the original image. We used here 0 padding, in fact. Do you see? We have 0 padding. So we will apply this one in that part, multiply values, and take summation and put it here. So it will be 0. Move 1 size, 1 step, stride equal 1. We will do it here. So it will be 1 times 3. It will be 3. Move 1 step here. So it will be here. So it will be 1 times 2 plus 2 times 3. So it will be 8. Move it here. So it will be 2 times 2. It will be 4. So in this case, the output, the size of the feature map, which is 4 times 4, it's the same as the original image, which is, it's not, okay? So we will go back here. I'm just expecting that we are putting here 0 padding. So, okay, we will come here. So it will be 3 times 3, it will be 9, okay? It will be 3, yeah. So it's the same size as this one. So 0 padding, when applying convolutional layers, we lose some pixels around the perimeter of the input image. It can add up for successive convolutional layers. One solution is to add pixels of 0 values around the boundary of our image. Stride by default. So if you didn't define, so Hussein, if you didn't define stride, it will be, by default, it will be 1.
Yes, of course.
So you need to know this, because don't say that we'll not have stride. We must have stride.
Yeah.
Because we need to scan the image.
Yeah.
So by default, stride
I
equal.
was searching for that. And also, there is a strides available in the sequential model.
Yes, it is, of course.
I found it, yes.
Yes, because we cannot do any convolution without stride.
Yeah. No, I thought that, for example, there is a default stride is equal to 1, just, and we cannot change. It is possible.
No, when the filter size is 3, you can select 1, I can select 2, I can select 3.
Yes.
But I don't know, can you select 4? In this case, we will skip some pixels. Is it possible?
I don't know. I'm running.
Yeah, you need to check it.
Yeah,
In fact, it is possible to skip 1 pixel.
Yeah.
So stride by default.
Sorry, Ibrahim.
Yes.
Yes, I just had like small comments. When you were speaking about the pooling, you said it's for reducing the overfitting. Or
yes, we will go to it, Ahmed. We will go to it. I guess it's the next slide. Yeah, so by default, the filter slides 1 pixel at a time, sometimes either moving, for computational efficiency, or because we wish to downsample. We move our window more than 1 pixel at a time, skipping the intermediate locations. So if you will increase the stride, you will skip intermediate locations, you will reduce amount of overlapping, so your algorithm will be more efficient in terms of computational cost.
Yes.
Because number of activations will be less. You can count number of activations. You can count how many activations here. This one, it's one activation, 3 or 4 activations and 4 activation. So it will be 4 times 4, it will be 16 if stride equal 1, right? If stride equal 2, number of activations would be less. And the number of activations is less. Computations is less, so it will be more faster. So it explains why it's faster when we change the stride. But overlap will be less, correct? So it will impact accuracy. So maybe accuracy will be higher or lower. You said it will be lower when you increase the stride.
Yeah.
Yes. Yes. So we can. So building blocks of CNN. So pooling layers. This pooling layers downsample previous layer feature map. You have a feature map here. This pooling layers, it does not have any parameters. It doesn't have any parameters. It should just do some very simple calculations, for example. So we have an image here, and we need to apply 2 times 2 max pooling. So imagine that we have a kernel of 2 times 2. So we will apply it here. When it's max pooling, it will return the maximum pixel value, right? So it will just give us 4 in this. So we will move one, if stride equal 1, we'll move by 1 step. We will take max from this one, so it will be 5. We will come here, we will take max, it will be 7. We will come here, we will take max, it will be 8. So we use max pooling to downsample, in fact, the size of the feature map. So we use it to downsample the previous layer's feature map. Pooling layers follow a sequence of 1 or more convolutional layer. So we can have 2 convolutional layers, and after that max pooling. We can just one convolutional, 1 CNN, 1 convolution, 1 max pooling, for example. So pooling layers follow a sequence of 1 or more convolutional layers and are intended to consolidate the features learned and expressed in the previous layer feature. It's like to summarize, for example, right? They compress or generalize feature representations and generally reduce overfitting of the training data by the model. Why it's reducing overfitting? Why it reduces overfitting? Why do we have overfitting?
Because it's too many neurons.
Yes.
Yes.
Yes. This is the only reason, in fact, because the model capacity. When your model is complex, it means your model capacity has high capacity. It has many weights, lots of weights. When we use max pooling, we will downsample the feature map, and now I need to apply another convolution here. Now it will be much less, correct? So number of activations will be less, number of neurons will be less, number of features will be less. So it will just make a reduction, and also it will have a huge impact in a fully connected layer. So even after convolution, in fully connected layer, it will be much less, because if I will apply max pooling several times, so it will reduce the feature map, the size of the feature map a lot. So at the end, when we finish this feature extraction, that we will use flatten, so the size will be something which can be handled. It will be just more simple. We can take some examples, for example, and make comparison. So imagine this one at the end here, after feature extraction, the size of the feature maps is 32 times 32. When we flatten it, it will be 32 times 32. If it is 64, the size will be different, right? So if it is 200 times 200, if we didn't use max pooling at all, so it will be very big, it will be huge. So it will make impact, it will make a huge reduction in number of weights, in fact, which will help us to handle this overfitting problem. So they have also a receptive field, often much smaller than the convolutional layer. Also the stride or number of inputs that the receptive field is moved for each activation is often equal to the size of the receptive field to avoid any overlap. We don't have any overlap. So in fact, we are moving here maybe with 1 step or 2 steps. We don't need to have overlap, in fact. But here he did some overlap, right? We can use max pooling. We can use average pooling, for example. When it's average, just to take summation and divide it, take the average of values, all values here. So it could be average, and it could be, maybe it's average, it has a meaning because it can like interpolate. So instead of using max value, we can just use average, for example. So pooling layers are often very simple, taking the average or maximum of the input value in order to create its own feature map. So the input here will be a feature map, the output will be a feature map, but max pooling layer will not have any parameters to train. So Ahmed, do you have any questions for?
Thanks, thanks. It has been clarified. Thanks.
Yes. So so they compress. In fact, they compress. You can just say that they compress or generalize feature representations and reduce overfitting. They reduce overfitting because we downsample the feature map, and when we downsample the feature map, we will reduce model capacity. In fact, number of weights will be much less. So we have, we have the input volume. This is the original image here. Maybe it's a 32 times 32 times 1. If it is one channel, we will have some convolutional layers, right? And it has some stride, max pooling, layer stride equal 2, which means there will be no overlap, right? And after that, we will flatten this one, correct? We will flatten it. Here we have 14 times 14, 14 times 14 times is 3. So just multiply it, multiply all numbers. So we will have this number of inputs, unique outputs, for example. We will use here fully connected layer. So we need to decide how many units here. If this number is too large, this one also will be too large, right? So number will increase because the number of weights here, it will be those number multiplied by this number. So if you can reduce this number a little bit, the total multiplication will be much less. So the model capacity will be much less. And when the total capacity is less, chances to overfit will be much less because maybe the model will not be able to memorize the data, right? So, so fully connected layers are the normal flat feed-forward neural network layer. It's like MLB. These layers may have nonlinear activation function or soft max activation in order to output probabilities of class predictions. Fully connected layers are used at the end of the network after feature extraction and the consolidations has been performed by convolutional and pooling layers. They are used to create final nonlinear combinations of features and for making predictions by the network. So at the end of the fully connected layer, it will be the normal MLB, which we used a lot for solving any kind of problem. But in shallow learning, for example, we need to do this feature extraction manually. So if you have some images, for example, you want to count number of fishes in an image, so you need to use some image processing techniques to try to get some features. Use those features for training your model. You try to make it easy. If you don't want to do this manually, you can just use those convolutional layers to extract features. And when you extract features, feed those features to your fully connected layers. So in fact, the brain is here. This is the brain. This is the one which will make decisions. In transfer learning, we import that part. I mean, if we are not going into transfer learning, so we need to build the whole model and train the whole model. We need to train all weights. If you will use, for example, like, I mean, last week, some people, they used the VGG16, for example, and they used YOLO. It's called YOLA? Yeah. So it's a pre-trained model. So can use this pre-trained model because this pre-trained model has been trained for maybe millions of images, and it's very good for feature extraction. And all images have something common. So I can just import any model which has been pre-trained, and I can just connect it with a new fully connected layer. This new fully connected layer, it will solve my problem. I will tolerate this one, tailor this one to solve my own problem, right? So this one will be designed for solving my problem. So for example, if I want to build a deep learning model for a nested data set, right? So I can import this one from VGG16, and I can connect it with fully connected layers. And in case of MNest, number of outputs should be 10. If it's CFAR 100, it's for object also, I mean classification, for example. So it will be the same, but we need to have 100 outputs, right? So I can import that part. And when you import that part, don't retrain that part again, because it has already been trained. Just import it, and don't train those ones. Just to train that one, only this one. Because if you will retrain this model, you will destroy it, because you don't have enough data, in fact, to train the whole model. So just import it and just train the weights of the fully connected layers. So this is transfer learning. We do transfer learning because there are many things common between images, right? And it should be possible to use AlexNet or VGG16, VGG19, whatever, because if they are working with images, so images have something in common. So maybe I can use the same with our problem. So the one which you need to play with, this one. How many layers here? How many outputs? And this is the one which we need to train using our limited data sets. Yes. In Keras, in fact, Keras provide an implementation of convolutional neural network called the Conv2D. It requires expected shape of the input image. You need to define the expected shape of the input image in terms of rows, height, column, and channels depth. So it will be like this one. We need to define this one. We need to define the input shape. So for example, if you are working with MNest dataset, this one will be 28, 28, 1. If you are working with CFAR 10, for example, I guess it will be 32, 32, 3. So we need to define this one here. If you are working with video, for example, so this video, it will be frames, right? So maybe this one will be the image, right? This one will be the image. So maybe it's 200 times 200 times, for example, 3. So the filter contains weights that must be learned during the training of the layer. The filter weights represent the structure of the feature or features that the filter will detect. And the strength of the activation indicates the degree to which the feature was detected. The layer requires that both number of filters be specified and that the shape of the filter be specified. So we need to specify a number of filters and also the shape of the filters to be specified. Yeah. So we need to define number of feature maps and the filter size. Maybe as the first convolutional layer, we will try to, I mean, maybe the filter size will be 3 times 3, number of features will be 64, right? So we need to specify for each layer, the filter size, stride, maybe if padding, for example, if you use padding or not, right? And also the number of features. So we will take break soon. So this is just a structure. We will get models. I mean, from Keras.models, we can get sequential and we can get model. Model, this is a functional API, and this is a sequential API. The sequential, it's much easier. Model, you can just use model when you need to make something more complex, in fact. Right? When you make very complex configuration, it will help you to build those, because it will help you to get access to some intermediate layers. So you can build really something, you can put some feedbacks, internal feedback, and make really something structure which is more complex. Layers, we have dense layer. This dense layer is a fully connected layer. We used the dense layer anyway before. We have dense layer, we have Conv2D layer, we have max pooling, we have dropout, right? So the model, I can select model sequential, for example. I can use 2 hidden layers. This one, it's a shallow learning, how we build it. So this is my model. We define a model as a sequential API. We add some layers. In each layer, you define number of units, type of activation function, dimension of input. This one, it's for shallow learning, or the fully connected layer. So the dimension here will be 100. So we need to flatten. If you need to use dense layer, you need to flatten your feature maps. For example, softmax, because we have 10 outputs, so we can use this one, for example, for MNest dataset. We need to compile, we need to define the loss function. we need to select optimizer and this matrix for evaluation metrics, for example. And after that, we can fit our model, we can train our model. We can use here history, equal model, dot fit. We have X train, Y train, number of epochs you need to define, batch size you need to define. And after that, after training your model, we need to evaluate our model. We need to predict, we need to check performance of our model. So we can just, I need to use it for prediction, right? So I have X test, Y test. I can use this one for evaluating my model, and we need to get loss, maybe loss and accuracy metrics. If you need to predict some classes, I can use it for X test. So the input will be X test. I can use it for predicting, for example, image data set. I have the X test value images. I will apply it to the model, and I get the output classes or labels. So we will take a short break, maybe 10 minutes, or we have some questions from online. So yes, Nicolo, can you talk, Nicolo, please, if you have any questions? Okay, so Nicolo, he was just answering Ahmed that max pooling, it's to reduce the feature map, the size of just for down sampling, and try to. Hamad, he has a question about flattening. Flattening, we need to use it before using a dense layer. So as you can see here, we have a dense layer. So the input dimension, it's just one number. It's not an image. In fact, it's just a vector. So the input here, the input dimension will be just a scalar value. When it's a scalar like this one, it means the inputs to this dense layer must be flattened, because this is the size of the 1D vector. I mean, the input to the dense layer, it's 1D vector. And this is the size of this vector. So before using any fully connected layer, we need to flatten our feature maps. We need to flatten it. Yes, okay, we will take a break, and we can start maybe after 10 minutes or 15 minutes. So I will stop. So please just get your coffee, and feel free. We have break until we can start at 10:30. 10:30 or 10:35, for example.
Are you planning to make some card plates?
Yes.
Or at least one?
Can we take picture? I can take picture from my car and print it.
Maybe that's enough.
Yes, okay. So I can take pictures of my car. You have also, can you take pictures from your car, from London?
Yeah, I think I can do that.
You can print it in.
Because first I tested with a Coco data set, which is the old ones from Web, just to test how it works. Yeah, so you see that. Yeah, it's quite accurate. Quite good. And then just use the on my TV.
Okay, yes.
So it's on the TV, but I guess it will be better if
we can print.
Yeah.
Yes.
Something like that.
Okay.
So we were wondering, since the OpenCV is a bit problem for,
we're wondering use YOLO just to extract every digit. Letter.
But is it possible to build a demo here in this screen? Have it running here?
That's my plan.
Yes. What do we need? If we need it to be running here all the time, can I ask? Should I ask Arna? Arna has those small computers. You know, this one which is they stick it to behind the screen.
Okay.
You know the small one.
Yeah, I think you sent me a link.
We can check it.
But just if we need to get it, I can ask maybe Arna or Gertz to give us one.
Yeah.
So we can stick it to the screen, connect it to the screen. We have the camera here. Do we have camera or not? We don't have camera. We need to get webcam.
Yeah, we should have a webcam.
Okay, so we can have this demo running all the time.
Yeah, it's very nice.
Can try.
And also, if some other, I wish if some other group, for example, can work for face recognition, it will be exciting. Because we have two screens here, we can have two demos running here all the time.
Yeah, that will be good.
So this is
Like, I think it would be easier to run it on YOLO to detect the letters and then trick it.
yes,
Kind of, because then you have RGB image.
it will be great
It will
because
much
we will be
easier.
running the original system. I mean, non-poisoned system. So now it will be able to detect all license plates correctly. And after that, we need to press a button. So it will misclassify it. So if
We will have to try it.
We will have to try.
yeah.
We can't promise anything now, but yeah, we will try. But when
Go for black box,
yeah,
for this white box approach.
Yeah.
White box approach, it's much, maybe much easier.
yeah, we're going for but yeah, we can try.
There is something called batch, universal batch. And this universal batch, I saw some papers, they print something in your glasses, for example, they put some marks here.
Yeah,
So when you,
some noise.
those dots or those graffiti, it will confuse a machine.
Yeah,
So,
yeah, we can try. Looking into it, it's quite complex.
yes, it's,
It's not easy.
but it will be nice
Hi.
if we demo
Hi,
here.
Ibrahim.
Yes,
Can I have a question?
yes, please.
Like I overheard you guys. Why would we want to misclassify like the number plate? I didn't get it.
Yeah, because it's a new direction, in fact, in security of machine learning models. So if people
Okay.
are using those machine learning models for making decisions, right, and in hospitals and everywhere, so can we attack those models and force them to misclassify things?
Okay.
So, for example, if you want to get loan from the bank, I mean, no, I will talk about myself, not you, for example. So I should not get a loan from the bank because my income, my history, and stuff like this. So of course, it's important for me to get a loan, right? So if we can attack those models, so they can classify me as positive, not negative. So it will be very good for me. It will be very bad for the bank. So.
Okay.
Ibrahim,
Mhm.
have you heard of the Enron dataset?
Hmm?
Enron
And
dataset.
Andra,
Enron.
what,
It's a data set of it was a company
okay.
that did something criminal, okay,
Mhm.
and then they did release 300,000 real emails
Mhm.
in the data set.
And is it public?
Yeah,
It's for images or for
no, for natural language processing.
natural language?
Yeah, so 300,000 real emails.
300,000?
Yeah,
700,000.
emails,
Emails.
internal emails
Okay.
people have written inside the company.
Yeah.
So it's like real emails.
Mhm.
So it's really cool fun.
Mhm. Because imagine, I mean, this also model which finally classify all emails into spam and ham. If you can attack those models, you can make big loss for companies and for people.
Yeah.
Either spend more time checking spam emails or
Yeah.
just losing some important emails coming
Yeah.
to their mailbox. So this is very, very good.
Yeah, you can extract important features and you can analyze positive, negative versus what happened. You can analyze communication. Really cool. But maybe you can use unsupervised learning since it's like 300,000 students a lot.
Can you share it with me?
Yeah, I can send you a link. And also this neural network here is quite cool. We're showing evolution of feature extraction because it's about getting color of cards. So it uses very high evolution layer to get the colors.
So it's only for colors?
Yeah, it's only for color classification that you see there.
It's really difficult to decide the color of a card.
No,
Yeah.
it's not. You get 95%. Yeah.
Do they have the public license?
Yeah.
Okay.
I trained this and I made it.
You made it?
Yeah. Like, I didn't make it, but I just made this architecture that works.
It works well.
I got 95%.
95. And what was the accuracy?
It was like 95%, around there. Like, yeah, 95.
So you got the same results which you did.
Yeah, I used values from there, so, but it only took 4 hours.
This is very good.
Yeah.
They published it in the archive.
But
I mean, they published it in the archive.
yeah, but they don't have posted GitHub for that many things.
And the training book, they provided link for the resolutions.
Yeah, those data set is public. But I wonder why do they split the network like that? What is the one?
This is one. Can you try with only one?
Yeah, I can try.
Yeah, because if you try with only one,
Yeah.
not just write a paper and you criticize this one, you can just say if we change it, make it more.
Yeah,
And now we get to see.
yeah, because it should get quite the same.
Yes,
I can try that.
and it can be by the way what's publishing in archive. It's very good because it's free and they can get lots of citation.
Well,
Citation. People
Yeah.
can cite your work a lot
yeah,
because it's free and they open access and people don't pay anything.
Yeah.
So they won't give sessions and maybe the first location will be archive. They will get lots of people from archive.
yeah,
Because if you need to publish it in a conference, you need to buy maybe $500, $600. If you want to go for a journal open access, you need maybe $2,000.
yeah. Yeah. Yeah, that's a nice thing. It should be open source.
Yes.
Out further.
Yeah, especially for some missions, those might have too much.
Yeah, I can send you the collab code.
Yeah, and the paper also.
Yeah.
Because I can make an example and.
Yeah. It's a good example, so you don't always have that 3 times 3 because you only see that almost.
Is it in Colab?
I've made this in Colab.
Very good, very good. So please just share the paper and the code.
Yeah, I will do that.
We'll have lots of examples.
Yeah.
right?
There is so much difference between reinforcement learning and deep learning.
Yeah, I guess it's different. Yeah, it's different.
We have to program and code something, or there is something in the Python for that, like a deep learning techniques.
There are some platforms, of course, but it's a model. In fact, it's a model which try to perceive. It has a function, reward function. So you try to detect, you try to get inputs from environment, and you have a function which give you rewards. Could be positive and actions, right? So you, for example, you have a robot, and the robot should need to decide if he will just move forward or left or right. So maybe the robot will just go forward because he has a target. I need to reach that target. So this is one cost function. I need to reach that point. If I will hit something, for example, so I will get negative. So I need to take another action.
Yeah.
So I train, in fact, I learn to perform. So you don't give the robot any information, in fact. It's like an agent, in fact. Yeah. So we will just perceive, maybe I have a camera and I try to detect, area around you, and you have a target which I need to reach. And you need to define a function like a cost function or reward function, for example. So, and I need to minimize this function.
Yeah.
And you have some actions, and I am free to select which action should I select. And you will train. So sometimes you will hit walls, you will hit chairs, you will hit tables. And at some point you will learn that this is not the right way. So you will learn how to move from point to point using this. So like, it's exciting, very, very important reinforcement learning effect. Very, very important. And there are some games, there are some platforms, in fact, games and stuff like this. So you can build a model and you can test it with those games, simulated environment, and try to, it's a very important branch, in fact. Yeah. Okay, so should we start?
Yeah.